Programmed contacts are normally closed. This examine this open, examine them closed only refers to contacts that are controlled by a physical input device. The textbook incorrectly uses the word register for the correct term word element. So this guy, when he wrote the book, for some reason, registers are inside the microprocessor. They're not in data files. They're inside the microprocessor, and we don't have access to a lot of them. We do have access to the status register that allows us to see errors that occur. So these are called word elements. So if you look through the documentation that comes with the actual that's available for the PLC, you'll never see the word register. We use non-retentive and retentive on-delay timers to create PLC ladder diagrams. So that's two instructions that we have. We have non-retentive and retentive. We'll talk about that as we go along. We're going to pick up an extremely powerful instruction called the move instruction. What we can do with the move instruction is we can take information from one data file and put it into any data file. So that's very, very interesting on what we can do here. What we'll do is we'll use this to create variable timers and variable counters. So we have constants. So in programming, we have what we call a constant, and then we have a variable. So in programming, what is the difference between a constant and a variable? Well, a constant is something you have to change. You have to change the program to change it. A variable means we can change the operand. So operand, have we talked about that term before? Because it's going to be used if you start reading these PLC manuals. So we have instructions, and then we have the numbers that the instruction operates on. So the numbers that it operates on, so if I said 3 plus 2 equals 5, then all these right here would be operands. And this right here would be the instruction. So we're going to get into, so right now we've been dealing with contacts. We hadn't been dealing with operands. When we start dealing with timers, we're going to have to deal with operands, which means these are the amount of time we want. One thing is the amount of time that we want the timer to count, right? So that would be an operand. So we have a timer instruction, then we say we want it to time for 1 minute. Well, that 1 minute would be a what? Would be an operand, right? Does that make sense? So the move instruction, we can make variable devices. So I can move information from one data file into another data file, or I can take a constant and move it in. We'll have to look at that when we get there. So basically our two categories of timers are on delay and off delay. And then those can either be retentive or non-retentive. And we'll talk about that when we get into it. Programmable timer instructions to interlock each other. So we'll look at how we can make a flashing light thing. We're going to cascade timers to increase the timer preset values because we're limited on what we can put in the timers. So we have what we call a fixed timer. We're not going to run into these in PLCs, but you definitely run into them in your house. Can change the time without modifying the program. A variable timer, the timer values can be changed without modifying the program. A single input timer, so this is what we have right here. We have single input timers. These are what RS Logic 500. So we enable the timer and start the timer with the same input. Siemens like to use double input timer, so we have a start timer and then we have an enable input. So we have two. So on a 2 input timer, if it's not enabled, it won't time. If you don't tell it the time, if it wants to the time, it has to be enabled. Does that make sense? Ours uses a single input, so that's what we'll look at to start off. So this is relay logic. So by the way, on relay logic, I'll come over here and I'll have a timer, and we're just going to do this. And then we have a coil. The coil does not define it as a timer. What defines it as a timer is the contacts controlled by that timer. So if I came down here on the next line and I came over here and did this, and then I put a like, then if I call, I'm just going to name this TR right now, and I'll call this TR. Then this symbol right here defines that as an on delay timer. So if the arrow points toward it, it's an on delay timer. If the timer points away from it, it's what we call an off delay timer. So what do we mean by an off delay timer? So what do you think an on delay timer is? Nobody's got any guesses? So if this is an on delay timer, when this run goes through, let's say I set it for 10 seconds. Well, this goes through, the timer starts timing, this contact stays open until 10 seconds and then it closes. So if I was to look at this at a timing, using a timing diagram, my coil goes through, this would be TR, and then this would be my contact. It would go through after the set time. And then when the timer coil goes false, this would reset instantly if it's a non-retentive timer. That make sense? So this would be an on delay timer. So my timer would be here. So we would call this, technically we call this a normally open timed to close. Now if I come over here and change this contact like this, I get to my pin. So that if it points in, this defines it as an on delay timer. Okay. Now this would be this is supposed to be normally open. This would be normally closed, timed open. What would happen here on my diagram, my marker is right on my recording software. And what would happen, this would be my contact, it would close. Then after 10 seconds, to do that. Make sense? This is an off delay timer. So an off delay timer, if I come over here, if we energize the coil, so this contact, instead of pointing like that, it would come up here and point away. This makes it an off delay timer. So what would happen is I would come over here and energize my coil. And then I come over here, this would be my contact. This is normally closed. So what would happen, it would start off like this. And it'll do that. And then it would come over here and do this. If I had my time set for 10 seconds. So its time occurs where? At the end. Now if I change this to a normally open, then the diagram would look like this. I'll leave the top the same. And contact would change states instantly. Then over here so this is the coil, and this is the contact. Then I come over here, when the coil goes false, this guy right here would do what? Would go out for this amount of time. So at a time, so an off delay timer times when the run goes false. An on delay timer times when the run goes what? True. Everybody understand that? Now these are relay logics. So if it points toward it, it's an on delay timer. If the arrow points away from it, it's an off delay timer. Now on ours, we don't have that. Our instructions are assigned from our instruction. We identify what type of timer it is inside the instruction. And the contacts are either going to be what? They're either going to be this one or they're going to be that one. And these are not examine if open, examine if closed, because these are going to be inside the program. These are not going to be controlled by a input. These are going to be controlled by a timer. Starts timing when the coil is energized. Drum becomes true. Normally open timer. Contacts open when the timer is finished timing. Timer contacts immediately revert to their normal state when the timer accumulated data resets to zero. Delay before contact switches when timers run on. On delay is switching when timers turn off. Off delay start timing when the timer symbol, or when the timer coil or symbol. So we're not going to use a coil. There's two methods used by PLC applications. We have what we call the symbol method, and then we have what we call the coil method. So the coil method, I would come over here, and it would have the same symbol as the coil, and then we would give it a name, timer 5, and then we would come up here and give it an address, right? And then down here we might put 15 seconds. That's the way we would set that up. We don't use the coil format. The Siemens Step 7, S7 application, and also the TIA portal gives you the option of which one you want to use. Step 7 uses nothing but coil contacts. So when they came out with the TIA portal, which is the new version, they gave the option of using the coil format and also using the symbol format. So it depends on which way you come up through it. RS Logic 500, we have absolutely no option on this. So this is a program and application, guys, and you can buy it. It's an interpreted. It's not compiled. I'm looking for. Here you go. Let's check it out here. This is an application called Logic Pro. It costs about $50 for a permanent license. But if you really want to learn RS Logic 500, this would be a good thing to play with. You can download it to a PLC because it's interpreted. It's not a compiled application. But it comes up sort of similar as soon as it loads. But what we have the ability to do with this is we can come up here, and so this is the project tree, but what we have right here is we have all these simulated inputs right here. Now this is simulating a modular PLC. So on a true rack-mounted modular PLC, the CPU module occupies switch 0. So this would be input 1. This would be output 2. This would be input 3. This would be output 4. Input 5, slot 5, output slot 6. So what I would do is basically the same thing. I could start a new run, right? And let's just put a contact right here. And then over here we have a section called timers and counters. We have T on, that's an on delay. We have T off, that's an off delay. We have RTO, that's a retentive timer. We'll look at it in a minute. And then this is where our counters are. We have an up counter, down counter, and then we got an instruction out here we call reset. So I'm going to pull the timer, I'm going to pull an on delay timer down. And notice we don't have an option for it to be a coil. It is a block instruction, right? It's a symbol. And what it's asking for is it's asking for an address. Time. Now, this guy doesn't give you the ability to change the time base. So first of all, I'll come up here and I'll set up a timer. Anybody remember the data file for timers? T4. Okay, this is the default, right? And then I'm going to put colon. And then we're going to put a timer number. We'll talk about that later on. Then I'm going to come down here and I'm going to put a preset. Preset is what you want the timer to time to. So if I wanted 10 seconds, I'm going to put 100 in here. Because the way this thing calculates the time, it takes the preset, multiplies it by the timer. So I take 100 and multiply by 1 that's what we're going to get away with that. On new PLCs, it's usually in milliseconds. So y'all have to understand that, right? So that's the way we set our timer. So this is an on-delay timer. So I'm going to come up here and I'm going to control this by an input. By the way, this guy don't use symbols, which I don't like, but that's okay. So here I'd have to put what? I'd have to put input. I don't know why my capital lock's not working. Input colon, I'm going to put 1/0. So what I've done, I've assigned it to this input module. I've assigned it to this switch right here. Now what you can do with this is you can right click and you can change that to a normally closed, you can change it to a normally open limit switch, you can change it to a normally closed limit switch, or just a switch or a push button. Okay. Then what I'm going to do is I'm going to come down here and insert another rung. I got to get back to the user. Oops. Okay. And then we'll put a contact. We'll assign this to a contact. Now, we'll talk about this a little bit, but we got two outputs available to us. We've got one called in, which stands for enable. We've got one called done, which goes through the timer time. So I'll come up here, I'm going to say T4 colon 0, and that's a bit, so I'm going to put done. So here, what's nice about this, and I'll show y'all where this is, we could actually address that. But what Alan Bradley has done is it's made it easier for us instead of going inside files that make up a timer. Instead of us deciding what that is, they give that to it done. And then I'll come up here and I'll put a coil out here. And I'll call this output colon. And one of my outputs I'll use 2. And then I'll use output 0. And then I'll download to my PLC. And then I'll go online. And let's see if this is working. I need to change this to a switch anyway. Oh, I'm sorry. I need to switch the PLC to run. Okay, so watch what happens now. So what I'm going to do is I'm going to come up here and enable the timer. The timer starts timing in milliseconds, right? And then it will get us up to 100, then the output went through. So this is our timer. Very easy. So we have a preset. What do we do with the preset? How do we come up with the time? We take the preset and multiply it by the time base, right? We got two things. What happened to the accumulator? So what I'm going to do is I'm going to come up here and turn this off. And you notice when I disabled the timer, the accumulator went back to 0. So what does the accumulator keep up with? It keeps up with the current time, right? Can y'all see that? Can y'all see it actually timing? So see, the accumulator is actually keeping up with the current time. And later on, guys, in advanced PLC, we can actually look at that and we can make things happen. Like it goes up to 10 milliseconds, but I can make things happen after it goes 5, 6. I can do that with advanced instructions, which we don't get to in this class. So this is a long delay timer. So let's go offline. And we'll come down here and we'll insert another rung. Oh, let's insert in 2 rungs. So insert 2 rungs. And then we'll use the same switch. So I'll come down here and I'll use input colon 1/0. So we'll use the same switch. And then I'll come up here and we'll go into my timers. And then I'm going to choose an off delay timer. Now notice it's the same setup. So we have a timer. That's where we're going to give the timer an address. Okay. Then we'll come down here and I'll put a contact that's controlled by that timer. So I got to give it an address. So we're going to put it in data file 0, and we're going to call this timer 1. Okay, are we okay? Because that's a little different from addressing. Then I'm going to set my time base to 100. We don't have the ability to change this multiplier on your PLC. You do. We'll have to go back and look at it. I think we have a 1, which would count in seconds, right? I think we have a 0.1, which would count in milliseconds, and I think we have a 0.01, or might be double 01, where we can really set fast time. So I'm going to assign this to that timer. I'm going to assign it to the done bit. So I say T4:1/what, done. And that was real nice that RStarget 500 allows us to use a name for a bit address. And then I'll come up here and I'll put another coil. And we'll assign this to another output. Output colon 0/2, Rich. 2/1. Okay. But see how much similar this is to the actual programming language, except symbols. We just can't use symbols, which is unfortunate because symbols make programming a lot easier. And then I'm going to do what? I'm going to download it to the PLC. And then I'm going to go online. Oh, I'm sorry. Then I got to switch my PLC to what? Run. So since we don't have the PLC, we have to do it on the application. So So notice the top timer is timing. And after 10 seconds, the output goes true. I found that out. Now notice the bottom one starts off with true. So it's an off delay timer. So what I'm going to do is I'm going to turn the switch off. And notice now this guy starts what? Timing. See that? And then after 10 seconds, this guy right here is going to go off. Make sense? Well, there's our 2 timers. Now notice on either one of these, what's the problem? So either one of these, so this one, when I enable it, it resets. On this one, when I disable it, it resets automatically. Everybody okay on that? Any questions? Okay, so let's go offline. And we'll put another rung in here. Put two more. And then we'll control it by the same contact. I know y'all need a break, guys, so let's do this. Okay, right. Input colon 0/0. And then I'm going to come up here on the last timer, and I'm going to put a retentive timer. Okay. Then I'll come up here, and I'll use a contact. Okay, so we have to give this another address, so we're going to call this T4:2. And we'll make this time for 10 seconds. Here's the T4:2, /done. And then I'll come up here and turn on another light. Output :0/2. Oops. Oh, the output :2/2. I've got RPLC on my mind. Okay. So we'll just pay attention to this bottom. So this is a retentive timer. So I'm going to, we can do that from here, by the way. So I'm going to download it. And then I'm going to switch to run. Okay. Oh, I did that too. I did it again. Let me go offline. Y'all see what I did? Input :1/0. Okay, so this guy's starting to count. This guy's counting. This is waiting for me to de-energize, right? Okay, because it's an alpha late timer. Okay. So this guy timed out. You can't see that output was three. We got three outputs. But watch what happens when I de-energize this thing. This guy reset to 0. This guy right here stayed at what? 100. Now what we can do with this guy, and I'll bring up one thing. So how do I get this guy to go back to 0? So here's my timer and cap. So we're not using counters. So I got on delay, I got off delay, I have a retentive on delay, I've got count up, count down, and then I've got that instruction number call reset. So what we have to do, somehow on a retentive timer, we're going to have to reset it. So I'm going to come up here and I'm going to put in a line. Oops. And we won't even pay attention to those other rungs. So I'm going to insert a rung. See where you insert it. Now here we'll use another input 1/1. And then I'm going to come into my timer, and I'm going to bring the reset out here. Okay. And then which timer do we want to reset? We want to reset timer 4:2. Okay. So we're going to show you something that the retentive timer does that the other timers don't do. So I'm going to download. We'll switch to run. Okay, I'm going to come up here and let's reset it. So I'm going to use switch 1. So now I went to 0. Well, what I'm going to do is I'm going to close the switch and timer stop. I'm going to open it. And what did this timer do? Well, this timer went to what? The top timer, as soon as I made the wrong faults, this guy went to 0. What did my retentive timer do? It kept the time that when I opened the switch. I close the switch, it starts timing again, I open it. What did it do? This stopped. This guy up here went to 0. I close it, right? Starts timing. So I can enable and disable my retentive timer, and it keeps up with the previous time, right? Until it times out. And then when it times out, the done bit goes true, right? You understand that? But what I have to do to this one to make it go back to 0? Well, I have to reset it. So you have to have a reset instruction for your retentive timer. You don't have to have it for your other timers because they reset automatically, right? So your off delay timer, your on delay timer resets when the run goes false. Your off delay timer resets when the run goes true. Your retentive timer, it's an on delay timer. It keeps up with the time. Even when the run goes false, it keeps the time. And what do you have to do with that to make it go back to 0? You have to reset it. Okay, guys, I'll take a break. What you're doing is you're putting your initials right here.
Right.
And so that means your numbers and everything are, since the space is so small, they're getting crammed, and some of your numbers are hard for me to read. So the only thing that's required here is just the lab number out here. So hopefully I wasn't talking about.
Interesting.
I'll have to. Timer for Allen Bradley RS Logic 500 data file T4 is reserved for timers, so you get that by default. Inside this, we can have addresses from 0 to 255. So basically, this kind of, since we're dealing with timers, we're not dealing with inputs. This kind of gets away from the way we address things. So the syntax for a timer address, we come up here. Then we put a data file number. By default, it's T4, but I showed y'all we can create more T4. We can create more timer files, right? Did I show y'all how to do that? I know I did, but I'll show y'all again. So this is why we have to specify. We don't have to specify. We don't have to specify inputs because those are physical. So we don't have to say. We don't have to say output 0, right? You understand? Because it's physical. But T4s, so I can come up here on data files and I can click right here and I can say new. And right here I can choose what type of data files I want. So that's a timer. Well, I can't use 4, so by default it gives me 9 because that's the next available one, right? You understand? And then we can give it a name, timer 2. And then I can say OK. So now I've got a timer 2 down here. I got a timer up here, and I got a timer 2. Well, now I got 256 more timers. So that's 512 timers that I can actually program if I've got enough memory in my PLC. So that's what you got to remember. Your PLC is not going to have an infinite amount of memory, just like this computer right here doesn't have an infinite amount of memory. And of course, what y'all probably keep doing on your phones is upgrading your phone just to get more memory so you can put more applications on your phone, right? So I had a 5S and I was running out of memory on the thing. I couldn't install any more applications without doing what? Deleting some of the ones I didn't use. So that's the same thing true with the PLC. It's got a limited amount of memory in it, and we can't just make an infinite number of timer files. So these, we don't have to specify a data file number because they're fixed. I can't add, the only way I can add more outputs is to put another module on here, right? Y'all understand that? But how many timer files can I have? Well, I can go all the way up to 255 over here on this on these data files over here. Now, fixed PLC, you can't add anymore. So if I was to bring up the 1000, I can't add any more data files. So what you get is what you get on those PLCs. So I don't need that, guys. So I'm going to come up here and right-click on that, and I'm going to delete it. Very easy to get rid of data files. So I can get rid of these data files. So if I never use any counters, but I want to use a lot of timers, then and I run out of memory, then I can delete data files that I don't use, right? Does that make sense? So this is the timer for the RSLogic 500. Here's our time base. So these are the times. So you click on this, and you got 3 time bases available to you. You got one. You got a multiplier of 0.01, and you got a multiplier of 0.001. So if you're dealing with seconds, then you'll use 1. But if you need something like 15.5 seconds, then you're going to have to use one of these time bases, right? Does that make sense? So if you do fractional times, then you're going to have to use a time base. Are we okay? I mean, I'm sorry, you'll have to use a different time base. I think every one that we use is going to be 10 seconds or 5 seconds or something like that, and we're not doing any 10.3, 4, 5, 6 seconds. So we could actually do something like that too with using these time bases. So timers are addressed T40. So we start off with T, then the data file number. By default, we get T4, but we can do what? And then we can come over here. We put a cover, and then we put a timer address or timer number would probably be, and this can be anything from what? From 0 to 255. So right now on my program, I use 0, 1, and 2, but I could literally go up to 255. Once I hit 255, if I needed more timers, I'd have to make another data file. Timers can be addressed. In theory, we can have 256 timers, but in practice, the number of timers is limited by the memory capacity of the PLC. By the way, each timer takes 3 words of memory. So we say 255. That's not 255 bytes. That's 255 times 3 times 2. So that's how much memory we could set up for timers. Multiply the preset. So first of all, the preset value is not the time. The preset value has to be multiplied by the time base to come up with the time. Y'all understand that? It would be the time if we use the multiplier of what? 1. And by the way, RSLogic 5000 did away with this, and Siemens Portal did away with this too. So RSLogic 5000 is in milliseconds. So if you wanted 10 seconds, you'd have to put 10,000 in there. Enable. So these are the flags that are available to us. So we have 3 flags that's available to us. A flag is either true or false. 2 of them we see on the outside. Timer enable. So if I wanted to address that, I'd put T4, then I'd put colon, and then I put the timer number, and then I'd put a slash, and then I'd put enable. Now that's a bit. We could address it bitwise, but what it does, it allows us to address these elements inside the timer by name instead of address. So if I wanted to address the accumulator, I'd say T4 0 dot, because it's a word, right? And then I could do ACC. I think it's ACC. I'll have to look at that. It might be ACCUM. I think it's ACC. So what RS-Logic 500 and 5000 gives us the ability to do on these words that's inside these binary words, instead of us know it's word 0, word 1, and word 2, it's going to let us address these by name. So this is a word. The accumulator is a word. It's a 16-bit word. So I have to put the dot out there, right? You understand that? So we have timer timing, which we don't see. We do see this one. So on our symbol over here, they give us enable, and over here they give us done. But we have another bit that's true anytime the timer is timing. And we'll use that too. We'll see what we can use that for. That's used every once in a while. And then we have what we call the done bit. This goes true when the timer has completed its time. So when the accumulator and the preset match, then the timer's done. So to address the timer's accumulator would be T4, then we'd put the timer number, so X would be the timer number, where X is the timer address between 0 and 255. If I want to address the preset register, or the preset word, excuse me, I'm getting into the book. So the books are calling these registers, but they're not, they're words. We would use T4 colon timer number dot preset, where the X is the timer address between 0 and 255. So these are actually, this actually came out of the RS-Logic 500, MicroLogic 1100 manual. And so these are the words. So if I really wanted to address this would be word 0. We could do it this way. I could say T4 colon 0 dot 2. And that would give me the accumulator. But we don't have to know that because Allen Bradley allows us to address it by what? By name instead of by address. If I wanted to address this enable flag, I could say T4 colon timer number, and I could put /15. But I don't have to do that, so instead of using that, I can use this, right? You understand that? So we could address them, but now you have to know what word element inside each timer. So each timer requires 3 words. And this is exactly. So word 0 would be flags. So flags we call them flags because they indicate when things are true and when things are false. And we use them just to indicate things. So they call status flags, by the way. Preset, you can address that, you can address that, or you can address them by name. So, whichever one you prefer. By the way, I think if you put that too, and you enter that, it actually adds the ACC after it. 3 types of timers: non-retentive timers, on delay, times while the rung is true, resets when the rung goes false. Retentive timers, on delay, times when the rung is go true, holds the time when the rung is false, but we must do what with this guy? To make it go back to 0. We have to use that reset instruction, right? Everybody okay there? Non-retentive off-delay timer, same as non-retentive on-delay timers. We do not have a non-retentive off-delay timer for this PLC. So this PLC only has 3 timers. It's got a non-retentive on-delay, it's got a retentive on-delay, and it's got an off-delay. It does not have a non-retentive off-delay. I'm sorry, we do have non-retentive off-delay. We don't have a retentive off-delay. Duh. So we already showed y'all that, right? So this would be a typical instruction. All of it in between here, this would be all our control elements. Right here we're using one switch, but that could be ANDs, that could be ORs, that could be exclusive ORs, that could be NANDs, NORs, whatever we want to do to decide when this timer is enabled. So that's our control device. Then we place our timer. We have to give it a what? We have to give it a data file number. By default, this whole semester we're going to use T4. We're not going to add any additional data files. Then I'm going to put a what? I'm going to put a colon, and then I'm going to put the timer number. When you hit enter, it's going to ask you for a symbol. So we're going to assign these things symbols. Then what we're going to have to do is we're going to have to select a preset. Y'all saw how I did that, right? You understand? I mean, I'm sorry, we're going to select a time base. And then we have to supply this. And these are going to be constants, guys, because right now, if I wanted to change the preset, I would have to go offline. I would have to change it. So a constant in programming means you have to take it offline to make the change. If it was a variable, it means I could do what? I could change it without doing what? Without going offline. We can show you how we can do that once we look at this instruction right here. That's a really powerful instruction. Move. The move output instruction used to copy the contents of 116-bit data file into another for loading a number into a timer's accumulator or preset word. So I can come up here and I could come up here and do this. So we'll give this an input. And then I can come over here and I use the move instruction. And it's a block instruction. And we have a source A. What I can do in source A is I can get this from another data file, or we can put a number in here to say 1,000. And then we got a destination. What's the destination? That's where we're going to put it at. So I could put T4 colon 0 dot preset. And what that would do is that would take 1,000 and put it into the preset register for that time. And we're going to show y'all something. This is why I want to use Logic Pro. I'm going to show y'all something really, really neat that we can do. Well, we can take the contents of any data file, and we can put it into that preset register. I could take the contents of any data file and put it in the accumulator. So I could actually change the accumulator. Instead of it being 0, I could put it at a number that I want it to be. So this is a really, really, really powerful instruction. This move instruction. Uses the contents to copy one 16-bit data file into another, or for loading a number into the timer's accumulator. So it's A68, by the way. So that's what it is. And preset register. Are we okay? So this has been an example of a move instruction. And y'all see that as it is not. So the first one says move 1,000 preset register, a preset word. The other one is a word. So this would be what we call, so this right here. I think I'm connected to my PLC. Let's make sure. So this is one thing I should check. So, I mean, you can go ahead and write your program. In fact, guys, if you know what you're doing, I could have this computer over in my office and I could write my program offline, right? You understand that? And then do what? So my PLC is here, so I'm connected to it. I'm gonna do this with Logic Pro. So I'm gonna do a new program, only available in the program mode. Do a new program. First thing it wants me to do is select the PLC, which really don't make any difference, guys, because the PLC is not actually out there, right? Then I'll come up here. They just want you to get, So I'm going to go over here and look at compare math, logic, program, control. This is what I don't like about Allen Bradley PLCs, is you got to scroll through this. On the Siemens programming language, they put it over here, and all your instructions are over there, and you don't have to go to this thing. I'm looking for the move instruction. Timer, input, output, compares, math, move. There we go. So it's a block instruction, source and destination. So what I'm going to do is I'm going to come up here and I'm going to oops. And we'll assign this to input colon 0/0. Then what I'm going to do is I'm going to come up here for my timer and put, insert another rung. And I'll put a contact here. Colon 0/1. No, I keep doing that, guys. I keep thinking about our PLC, but this is a modular PLC /0. Input colon 1/1. And what I'm going to do is I'm going to come over here and put a timer. And the address 240, we'll use that, that's fine. This one, you don't have the, on Logic Pro, you don't have the ability to change the preset. So if I wanted to count to 10, in fact, this is not going to make any difference. So what I'm going to do up here is my source. I'm going to say input colon 3. Down here, I'm going to put it in T4:0 dot PRE. So what's this guy going to do? So I'm going to come over here now. We'll go ahead and go offline. So this move instruction, we're going to download it. Right, I'm going to switch to run. And I'm going to come over here and just randomly select switches. And you can see this is changing up here. So that would be a binary 13. And we'll come up here and randomly select switches. And then what I'm going to do is I'm going to come over here and energize this guy right here. And can you see what the preset did over here? So we literally, with the move instruction, so this is definitely available. So with the move instruction, let's see if I can, I'm going to reduce this, because we're not using those anyway. And that's as big as this will go. So what I'm doing with that move instruction, I'm taking the content of the word, and I'm putting it in. When I go over here, move those pieces over there, so we'll come over here and take that right there and convert that to decimal, it would be what? 437. I can put anything I want to into this timer. So every time I come over here and make this input true, it automatically does what? Loads that into this timer's preset register. So this move instruction, we can take an input port and we can make this totally a variable, which means I can come over here anytime and change that. So the move instruction is very, very important. We can take any data file and put it into this guy. So I could take the contents of a counter's accumulator and move it into the preset register of a timer. So we can move the contents of any 16-bit data file into another 16-bit data file, no matter what. I can take the contents of the preset register on a timer and move it into a counter. I can take the contents of the accumulator on a timer and move it into a counter. So that move instruction allows us to take any data file, any 16-bit data file, and put it into another data file no matter what, no matter where it's at. That makes sense? So in ours, all we're going to do is set up in ours, all we're going to do is have what? We're going to have two move instructions, and then I can come up here. I didn't want to do that. And depending on the move instruction, it allows us to change the contents of the. So it is ACC, guys. So I've got that wrong 2 places in here. So I need to go back in. That's wrong. So here, when I close switch 1, it's going to load preset register on 1,000, what about low? What's it going to load? What if I close switch 0 and switch 1 and switch 2? What would it load? So how does the scan go? Scan by 0 first, 1, so it loads to 1500. Because it scanned what? It scanned second. Reset instruction used to reset on delay retentive timer. It sets the accumulator to 0. You ever looked at that, right? So on a retentive timer, you're going to have to reset it. Now over here, we're going to reset it with a switch, but we could reset it with another timer. We could reset it with any device that we can put in here that we need to reset it. PC11 that I'm using an off delay timer. We've already showed y'all that. Interlocking timers. So what we have the ability to do is we see in industry all the time. You see what lights doing what? Flashing. Or we have cycle timers. Cycle timers means so when I have a timer I put on my Christmas tree, my outside lights during Christmas, and it turns them on at a certain time and turns them off, but it does that every day. So we'd call that, what we call that is a cycle timer. So it's constantly running, and it does things in a what? It does things in a cycle. So it's like the timer on your washing machine. So you start the time, and what does it do? It fills the water, then it does what? Yeah, so it does, and then it washes, and then it does the spin, right? You'll understand that. Well, cycle timer. So cycle timers means as long as they're activated, it's going to do off, on, off, on, off, on, off. A lot of times we'll use these just to flash lights. So to get an interlock timer, then what we do is let me bring this up. Is we use the timer timing. So this is something you have to know because it's not one of your outputs. So notice I'm using a normally closed timer timing. So timer 1 is looking at timer 0 controlled by timer 1. Timer 1 is controlled by timer timing 0. Okay, does that make sense? So we enable that. Timer starts on. Let's see if I got this program. I think I do. that. I don't know if this is it or not. Nope. I don't know if I can do this or not. So, nope. Yeah, it did. Oh, I didn't assign an output. So we'll assign this to output code. And it's good to run that because sometimes your program gets real long and you'll forget things like that. Okay, so now we look good. So this guy is controlled by this guy. This guy is controlled by that guy. So my switch is already closed, so it came up and started running automatically. Where's the Something's not working. This guy right here is staying true all the time. So when this finishes timing, so it's supposed to stay on for 5 seconds and off for 5 seconds. Oh, duh. Let's go duh together. Duh. Timer 1/timer timing. Oh. I was using the timer. I did that again. Did that wrong again. I'll get it right in a minute. I'm trying to get in a hurry. So these are normally closed contacts. Normally closed contacts. This is timer 1, timer timing. And this is timer 0, timer timing. Oh, I did that wrong again. Okay. I'm going to take care of me. This is timer 2, timer timing. And this is timer 1, timer timing. Let me check it for errors. Okay. So first of all, I was using the done bit instead of the timer timing bit. You see what's happening? The phone timer 0. My light's coming on. 1 second. Pull it off. Pull it off. No, this is fine. Timer 1 time. So we'll swap it back and forth. This is called interlock timers. These are cycle timers. So if I wanted something to happen in a cycle, then this is the way we would do it, right? You understand that? We just interlock these 2 timers, but you got to be able to understand why we do not cross couple, because what we're doing is one of them's energizing the other. When it gets through, it energizes the other one. It stops timing, energizes the other one. It starts timing, right? And you set that clock and does what? Goes back and forth. So this would be a cycle timer. So a cycle timer does what? Time, off, on, off, on. And we can make the on time different than the on time if we wanted to. All I would do was just figure out which one was on and which. So here, my own time is controlled by this timer right here because I'm using the timer timing off of timer 0. So we okay? So I'm sorry, I just try to get in a hurry, and I'm sure y'all do the same thing. First time I used the done bit, and then I was trying to call this 0 and 1, but I called this 1 and 2. And how long would this run? Until we stop it, right? And of course, it'll go through one timing sequence, and then it'll stop. These are called interlock timers. Now, the problem we have with this, and we're going to have to, the problem we have with this, and this is what we have to understand, is this guy uses signed numbers. And we talked a little bit about that. I know it's kind of confusing. But what happens is that if we're using signed numbers and we got 16 bits, then what we do is we lose the most significant bit. We lose the most significant bit for the signed bit. So if it's a 0, it's considered a positive number. If it's a 1, it's considered a negative number. So this is going to be a positive number. Well, what that means is instead of getting 16 combinations, instead of getting 16 to the 16th combinations, which is 65,536, then we're only going to get 2 to the 15th, which is 32,768. Now, why can I only have a positive number up to 32,767? I can have negative numbers up to a minus 32,768, but I can only have positive numbers up to 32,767. Well, you sacrifice 0 has no sign. So 0, the most significant bit on 0 would be 0, which we'd say is positive. We say it's a positive 0. There's no such thing as a positive 0. So 0 takes up one of your positive combinations. So that means the maximum number I can put in my preset register is 32,767 for these timers. If I try to put 33,000, it would give us an error, right? Because it would try to be timing negative. We can't time negative. Everybody okay? So the biggest thing I can put in a preset, whether you understand it or not, the biggest number I can put in that preset register is 32,767. Well, what if I needed the time to 35,783? Well, we'd cascade timers. So we'd let one timer, when it got through timing, it would do what? It would start a second timer. So we'd cascade timers. So if I need to exceed the range on the timer, or if I need to set up a sequence. So let's say I want something to happen after 5 seconds, and then I want something to happen after 10 seconds, and I want something to happen after 15 seconds. But what I could do is I could come over here and set up a timer, and I could set it up for 15 seconds. Okay, understand? So let's say I want this to happen after 10 seconds after this one. Well, what I would do is when this one was done, I would do what? I would trigger this one with that one, and then I would trigger this one with that one. So we cascade timers all the time. So if I wanted something to happen in a sequence, so if I wanted something to happen after 10 seconds, and then I wanted something to happen 10 seconds after that one finished, right? You understand? Then what we'll do is we'll do what we call cascade timers. If I want to exceed this range of 32,767, then I would cascade timers. In fact, I probably wouldn't go to 32,767 because that's a hard number to keep up with. I might cascade at 10,000. So that way, that 10,000. So this is cascading timers. This is not timer. So here they use timer done. These need to be a normally open contact. Change to normally open. So what would happen is I start this switch right here. This guy starts timing. It's time to set for 25 seconds. Everybody understand why? Can y'all see that? Because it's got a time base of what? 0.01. This timer starts timing. When it gets through, it says it's done. This would close. This timer would start timing. It would time for 30 seconds. When it got through and its done went true, it's through timing, this right here would go true, and this timer right here would start timing. So this is going to occur 25 seconds. This is going to occur 30 seconds. This is going to occur after this one gets through, and this one right here is set to time for 10 seconds, but it doesn't time until this one gets through. So it goes like this. So this would be if we want things to occur in a certain sequence, right? You understand? A time sequence, then we use cascade time. Does that make sense? Everybody okay? So what we use here, we use the done bit. We don't use a normally closed. If I use a normally closed, they'd both take off and count at the same time. So this is figure 8-6, so that's wrong in your text. They both start. So these guys will start counting right off the bat, but that's not the way it works. So we want the normally open timer done. So when does the timer done go true? When the timer does what? When it finishes timing. And of course, when I open this switch, this guy will reset. It won't be done anymore. It'll open that. It'll open that contact. This guy would reset, and this guy would reset. So all three of these timers would reset when we open that input. So this is cascade timers. So what do we use? We use these for what we call sequencers. Sequencers mean you want things to occur in a what? In a sequence, right? Does that make sense? Cascading on delay timers, that's the same thing. And that's timers, guys. So what's the three types of timers we have? Two categories. We have two categories. What's the two categories? Somebody said off delay and on delay. But we have three timer instructions. We have a what? We have a non-retentive on delay. We have a non-retentive off delay. And then we have a retentive on delay. So your non-retentives, those guys are going to reset instantly, right? Okay. Your retentive, you're going to have to do what? You're going to have to reset it. So there's our timers. So we use timers all over the place. We want things to occur at a certain time, right? Industry does that all the time. Like just think about the number of timers you have at your house, in your car, right? Especially in your house. So, you have a timer for your oven. You have a timer on your microwave. You have a timer on your coffee pot. You have a timer on your washing machine. You have a timer on your dryer, right? Just those, just in your house, that's all the timers you have. What would you have to do if you didn't have that? You have to manually do that, right? You'd have to go in and manually do everything. So now it's all, you have timers in your car, right? So right now, if I turn my ignition switch off and my radio is on, it stays on for what? It stays on for a certain amount of time, and then after a while, it'll do what? It'll turn itself off, as long as my key's in the ignition. A lot of cars have timers on lights, on dome lights, on your main lights. We have timers on that. Some of y'all have timers on your fan out there. So it runs a little while even when the motor's what? Turns off. So if we can't do without them, then the industry's not going to do without them, right? And these are really, really neat. They replace a lot of mechanical timers that we use in the. So any questions on timers? Block instructions. So we have to do what? We have to understand the type timer. We have to assign it an address. So right now you use the data file form. We put code in and we put a timer number out there. I understand. Then we have two because they were very interesting. Preset is very important. It's not the time, it's the baseball time. There's the time, I have to take that and multiply by our preset, right? And I'm sorry, our time base. That's a little different on this time. Those two times is the way that time base. We got three status flags we can look at. We can look at the table, which is very important. This guy right here a lot. So this shows us when the timer has the preset and the accumulator match. So the timer's what? Timer's done. And then what's the other one we got available to us? Timer time. So on those interlock timers, that's the one that we use. So that is going to be true anytime the timer is timing. This enable is going to be true anytime this rung is true. So we use a single input for both our enable and our start timing size. A 2-input timer would have another input, and it would be called enable, and then the other one would be called time or something like that. So that would be what we call a 2-input timer, which is what Siemens likes to use. Are we okay? Any questions on timers? I understand the 37,767. And the names. So what are the names? So we can address these things by name instead of actually knowing where they're at inside those data files. So with T4, X, and if I want the accumulator, I'll put a .ACC because that's a 16-bit register. T4 colon this, PRE, that would address the preset, right? And we're not going to use that this semester. But later on, we get into compare instructions, and that if you take PLC2, where we can say if the accumulator is equal to 30, which is pretty good. Then we have T4X slash ENE, so that would address the enable bit, right? T4 colon timer number slash DN, that would be the done bit. T4X slash TT, that would be the timer timing. So this is the way we would address these registers and these address these words in the program. Everybody okay? So counters, what type of counters do we have? Huh? Counters. Oops. We have two types of counters. What would you think they would be? So we can count two ways. We can count what? So what is a football game? What does that clock on the football scoreboard do? Does it count up or count down? Okay, so we need to count down, right? Then we have other things, other types of counters that we want to do what? We want to count up, right? So that's our two counters, guys. We got up counters and down counters. And they're available right here. So they're in the same section. They're in the same, so right there, timers and counters. So CTU, what do you think that stands for? CTD, what do you think that stands for? Countdown. And then reset. We'll have to use reset. All your counters have to be reset. We'll have to use the reset instruction. So we use the reset instruction for two things. We use it to reset retentive timers, and we also use it to reset our counters. By the way, we might have a group coming through. Alabaster is looking at offering some training through their high school. So they might be dropping through to look at our labs. So this is chapter, I don't know, wait till it loads. It should be the one right after timers. Similar to timer input, timer instructions displayed in block or full format. Of course, we're going to use the block format. We're going to use single input. So all ours use single input counters. So the enable and the count is exactly the same thing. Count up, count down. Everybody understand those? We'll see. Arch logic is weird, by the way. Preset. The preset data files. This is where we're going to count to, right? Or count from or count to. So accumulator, this is going to hold the current count. And then the status word, this is going to tell us when it's done, when it's enabled, if you have an overflow or if you have an underflow. An overflow means the maximum we can count to is 32,767. Well, what happens if you count past 32,767? Well, the number becomes negative. So we'll get what we call an overflow bit. So an overflow would indicate that we've exceeded the range of positive numbers. Then if we're counting down, if we go minus 32,768, and we do one more down count, the number's going to go positive. Well, we call that an underflow. So we have two additional flags. We have overflow and underflow, which tells us if we exceed the maximum range of the signed numbers. So count up, count down. So these are our flags. We got the count up, count down, which we don't use very much. We have the done, which means the counter, the preset, and the accumulator match each other, right? You understand that, so it's through counting. We have an overflow. So true when an up counter accumulator exceeds 32,767. We have an underflow. This is true when a down counter's accumulator exceeds the minus 32,768. We have a update accumulator bit, which I've never used. Oh, these are high-speed counters. These are hard. What they found out is that these counters are programmed. So we come over here and we put a counter. But over here, this is going to be a machine code program, and it's going to be very, very long when this is downloaded into the PLC. So we tell it a counter, but the counter has to run a machine language program that could be very long. And what was happening is that when we were counting, we would miss counts. If we tried to count extremely fast, the program could not keep up with what we were trying to count. So the big advantage of hardware is faster than software. What's nice about software is we can change it. But what they've literally had to do is they've had to put hardware counters back into our PLC. And we call them high-speed counters. These are literally hardware counters. So it can keep up with what? Keep up with the demands that I don't know if I've ever seen, we worked on a Go Flake dog food up there, where they make dog food, and those cans would be flying by, and they'd be going by so fast they would look like it was a solid line. And they would have to do what? They would have to count those things. There's no way in the world a counter instruction for any PLC out there could keep up with those. So that was the problem they had. So they realized right off the bat that some situations we cannot do with software. So they've literally put high-speed counters back in. So what you do is you read the accumulator every once in a while. The counter never misses a count, but you'd go out there and read it every second or so. Your count would update. But those suckers don't miss a count. So we have high-speed counters. I don't remember how many's in this one. I think it's got like 3 or 4. But that's available to you. And it's on one of these inputs. So it'll tell you which input you would use for your high-speed counter. So every PLC that we've had for quite a while supports these high-speed counters. So counter reset. Once the counter accumulator matches or exceeds the preset value of the done bit is set, the counter will continue counting. So these counters, if they are counting and you have the preset value set to 10 and it hits 10, the done bit will go true, but the counter will keep counting. So the only way you're going to clear the accumulator on a counter is to reset it. Y'all understand that? Because we don't want to lose counts, right? You understand that? So a reset output instruction must be used to reset the accumulator to 0. A move instruction can be used to set the accumulator preset to any value besides 0. So we can use that too. So here's our data files, which the book calls registers, but they're data files. So we address them. So by default, the data file assigned to counters is C5. Then we give it a counter number. The counter number could be from 0 to 255, right? And then we have these flags in these registers we can address. So C5.preset, that addresses the preset register, not preset word. C5.acc addresses the accumulator word. C5 /T, this is count up, this is count out, this is done, and they left out a couple of them. They didn't give us what. So if we wanted to monitor the overflow, we would say what? C5 counter number, and then we'd put overflow. And then if we wanted to address the underflow, it would be C5:X/UB, which they don't give us in this chart. And that's very, very important, because if you don't monitor that, then you could literally have problems, right? Because what would happen when you're on an up counter, if you had a 32,767 and you went to 32,768, it would go negative. So we can monitor that. Accumulated word element increments when the counter input device changes state. So we'll just do this. So let's come over here. We'll bring up 500. I'm going to come up here and I think I saved this, right? Yes, I did. I'm going to create new. We'll come and do that. We'll select the CPU. It's going to be. We'll just insert. Right now, I'm on up counter. I'm going to insert a rung. And then we'll put a push button in here. And then I'll come over here, go to counters. I'm going to do an up counter. And so there's our information we got to put in there. Okay. And I'm going to assign this input colon 0//0. And we'll call this guy count. And by the way, y'all saw once I assigned the timer a symbol, I didn't even I could say timer 1/done, right? And you say that instead of having to know the address. We'll come up here and assign this to C. We'll assign this to C5 colon, and we'll call it counter 0. What do we want to count to? Let's make it short to start off with. And then I missed the symbol opportunity. Okay, so we'll check this for errors. Okay, it says we have no errors. Then I'm going to download it and go online. Call it counter FMO. Okay, so we'll come up here and we're going to start counting with switch 0. 1. I'm gonna do momentary. So momentary is to the right? 2, 3, 4, 5, 6, 7, 8, 9. So my accumulator and my preset match. So what happened? My done output went true. Well, what can I do? I can keep counting. My done bit stays, my done flag stays true all the time because now if we meet or exceed the preset value, the done flag will be true. So if I want to go back to 0, what do I need to do? So let's go offline. And then we'll come in here and we'll put another one. And we'll figure out how to do this. Right now I'm using a switch to reset that thing, but we could let the counter reset itself. So I could use the done flag to reset the counter, right? And make it reset at that value. And we might do that. User, I'll bring this in. I'm going to bring a switch in. I'm going to call this input :0/1. I'm going to give it the symbol, I'll just call it reset. Counter. And then we'll come over here and I'm going to go to counters and timers and I'm going to use the same reset instruction, but I'm going to reset T5:0. I don't know if I can assign it a symbol name or not. I'm going to do that. I didn't get an opportunity to assign it a symbol. Okay. So now what we're going to do is we're going to download it. It wants to give us a revision number. Give me a second warning that I'm fixing to wipe out whatever program I have in the PLC, right? Okay, the processor's in run mode. We can't download a program in run mode. We have to switch it to program mode, but we have it on remote, so it's going to do that for us. Okay. Then we do want to switch back to run mode, yes. And do we want to go online to monitor it, yes. And so this is what we got. So I'm going to come up here now. I'm going to flip the switches. And you see it gets to 10, the done flag goes true, or the done bit goes true. Keep counting, but when I come up here and flip this, then it resets. But I'm using a switch. But if I use the done, I could use the done down here, and it would automatically do what? It would automatically reset it when it was done. I could put a decision out here. I could put an and. If this counter's done and this counter's done, then reset both counters or stuff like that. So we can put parallel reset instructions and reset several counters. So what I'm going to do, sometimes RSlogic 500 lets you do things while you're online, by the way. Let's see if it lets us do this. So I'm going to see if I'm going to put 37,000. I'm online. I'm going to put 32,763. So it let me get by with that. So sometimes, even though we say we have to make changes, even though that's considered a constant, sometimes you can get by with that on RSlogic 5,000. So let's see what happens here. I'm going to come up here and my preset, I'm going to put, I'm not going to count that far. I'm going to put 37,000. 60. No, it didn't let me get by with that. So, what do I need to do? I'm not going to count that far, guys. Yeah, I should have went. So, 32,760. Let's see if it lets us get by with that. Oh, yeah, good. Thank you. So, we'll come by, and so it let us make those changes online. So, I'm going to come over and start counting. 66, 67, and what happened? They went negative. So I just had an overflow. Right? You understand that? So if I monitored that bid and I did something about it, then we would be okay. But what we could do is we could actually set the done bid to start another counter, right? You understand that? Does that make sense? So we could say when this got done up to 30,000 instead of that number, I could start another counter and let a counter continue counting. We could do tens of thousands to make it easier to keep up with, but that limits this guy right here to this range of counts. So I just wanted to see that. But if we looked at the overflow flag, we would see that it did what? It should have said. So I can still reset it. So this guy right here lets you change the contents of the preset in the accumulator while you're what? While you're online. Oh, that's interesting. So count up, looked at that, talked about the reset instruction done. We okay there? So your counters you have to reset, right? Count down. This is a weird guy. So this is what we have. So what I'm going to do is I'm going to come over here and I'm going to go offline. So I'm going to start a new program. Yes. I should put up, down. Oh, sorry. It was telling me you didn't need to be online when you saved it. So Micrologic 1100. Oops, wrong PLC. And the problem is if you choose the wrong PLC, it will let you do a program. You can do the whole program. It's just that when you try to compile it over, you'd get the error, right? So we're going to come up here. I'm going to insert a rung. I'm going to come over here and put this. And over on my counters, I'm going to do a down counter. Call this guy input :0/0. We'll call this count. We'll come over here and call this counter 5:0. Call this counter 1. Okay. And we have a preset value. So this guy's going to count down. So let's put a positive number in here to start. Hope you'll let us change it while we're online. And I'm going to come up here, check it for errors. It's okay. And now I'm going to download it. So I'm going to download it, give it a name. When we were using DOS, your file names were limited to 8 characters. And you had to come up with an ingenious name. I think RSLogic, I think this is 24 or so characters, so we can pretty much well name the file what we need to name it. Okay, guys, so I've got it downloaded. And what I'm going to do is I'm going to come over here and start counting down. What's the problem? My accumulator is counting down from 0. So right off the bat, it went what? It went negative. So now I'm going to have to go all the way around. I'm going to have to go to minus 32,768 and count all the way back till I get to a positive 10 before this happens. So that means what we need to do is, if it lets us do it, is we need to start the preset with a negative number. Now I'm going to come over here and I'm going to set this to 0. So this guy, when you count down, the accumulator is actually what's counting down. So if you start the accumulator at 0, it's going to go to a -1. So that means your preset number needs to be a what? A minus number. So that gets people confused. Okay. So we got this set to 0, so I'm going to come up here. Now notice what happens is the done bit starts set. So the done bit is telling me that my accumulator meets or exceeds this value, right? You understand? So that's different. So a down on an up counter, your done bit starts off clear. On a down counter, your done bit starts off set. So here we go. -1, -2. Let me get off that so you can see it. -3, -4, -5, -6, -7, -8, -9, -10. So I wanted it to count to 10. I've just counted from 0 to -10, and the done bit is still true. So on the down counter, you've got to make it more negative. You don't have to make it match. It's got to be more negative. So when I go to a -11, the done bit clears. That makes sense? So that's weird. So if you wanted a count of 6, you would have to load the preset with a minus. If you wanted a count of 6, you would load the preset with a -5. If you wanted a count of 50, you'd load the preset with a -51. Or we could do it this way. That's the way the book teaches. I could come up and do it this way. So instead of loading the preset, I'm going to load the accumulator. And then I'm going to set the preset to 0. So now this acts like a down counter to me. But we reversed our register, we reversed our files. So now when I start counting, it goes to 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. But you still got to go one pass. So on a down counter, you have to load the register with one less than you want to count to. So if I load the accumulator, I can start with a positive number. If I load the preset, I have to start with a negative number. Does that make sense? So whichever one you want to do. But you always got to go one less than what you want it to count to. And the done bit starts off set. And then when you exceed the count by 1, you come one negative, or actually less than one negative, then that's when the done bit clears. And this is, they kept this on Studio 5000 also, this weird down counter. Siemens don't do this. Siemens counts down. So y'all see the difference. So if I come over here and load the preset register, I'm going to have to load it with a negative number. And then the accumulator, by default, the accumulator sets to be 0. Everybody understand that? And then I have to do what? And then we have to go one more count. 10. One more count. Everybody okay? Or I can do what? I can put 0 in the preset. Then I can put a positive number. So if I wanted 10 counts, I would put a 9 in there. And then we come down 8, 7, 6, 5, 4, 3, 2, 1, 0. So on a down counter, your accumulator has to go negative in respect to but it keeps counting though. Right? So how would that clear this out? I'd use a reset. But what does the reset do? The reset resets the accumulator. So it would go back to 0 and you'd lose your positive number. So how can I take care of that? Well, I would use a move instruction. Instead of using a reset, I'd use a move instruction. And what can we do with a move instruction? We can take anything we want to and stick it into any data file. So that's down counters, guys. That's our 2 down counters. We have 3, of course, if I come up here and load this with a minus 32,760, 765, and then this right here has a minus 32,760. Then we download it. Oh, we don't have to download it. Sorry. So what's going to happen here? $768. One more count. What did it do? It went positive, right? So that would be, here we'd use the underflow hit to decide what we need to do. So we're okay on counters. Pretty simple, right? Timers, we only got 2 types of counters. We got a what? Up counter and down counter. We don't have an up-down counter. Some of your PLCs give you an up-down counter, which is really cute. That's really neat. This guy doesn't have to, we have to simulate that, and we're not going to get into that today. So any questions on counters? We can cascade counters, we can cascade counters. Like it needs to jump, so we cascade counters. We don't cross couple counters or interlock counters, but we definitely can cascade them. That makes sense? Alright, guys, see y'all when? We'll be in what? Lab. Yeah, Monday we'll be in lab. Next Wednesday we'll be in lab. Monday after that we'll be in lab. Wednesday after that, I think the Monday after that we'll be taking test 3. Then after that we'll be, Then after that we'll be doing the 5.